Today, we're going to trace the incredible, almost magical journey your message takes from just a thought in your head to a signal that flashes across the entire globe at pretty much the speed of light. It feels completely instant, right? You hit send and boom, it's there. But in that tiny fraction of a second, your message goes through this series of wild transformations. It's a journey through tech that would have seemed like pure magic just a generation or two ago. So let's pull back the curtain and break it down step by step. All right, so where does this all start? Well, it all begins with something physical, like the sound of your voice. Before we can send it anywhere, we first have to translate that physical reality into the language that machines understand. So when you speak, you're literally making waves, pressure waves in the air. A microphone's job is to be the first translator in this whole process. It feels those vibrations and turns them into a matching electrical signal. You can think of it like an electrical mirror that's perfectly reflecting your original sound. This electrical copy is what we call an analog signal. Now the thing is, that analog signal is kind of fragile. To make it tough enough for a long journey, we've got to make it digital. Imagine you're trying to capture the motion of an ocean wave by taking pictures of it. The more snapshots you take every second, the more accurate your final picture of the wave's movement will be. Well, that's exactly what sampling does. For a CD to capture all the sounds we can hear, it has to take 44,100 of these snapshots every single second. So you might be wondering, why go through all this trouble? Well, it all comes down to one word: resilience. Think about photocopying a picture, then making a copy of that copy, and so on. Every single version gets a little bit fuzzier, a little more degraded. That's analog. Now think about copying a file on your computer. The millionth copy is absolutely identical to the first. That's digital. And that resistance to noise is what makes it possible to send a crystal clear message across town or even across an ocean. And what's doing all this heavy lifting with these ones and zeros? Meet the unsung hero of the modern world, the humble transistor. Just think of it as a microscopic light switch. When a bit of voltage hits it, it flips on, and that's a 1. No voltage, it's off, and that's a 0. Your phone's processor has billions of these tiny switches, all flipping on and off billions of times a second to handle your now digitized message. Okay, so our message is now this long string of ones and zeros stored safely in our device. But how do we get it to leave the device? How does that digital information actually fly through the air? Well, it needs a ride, and that's where radio waves come in. Think of it just like sending a package. First, your device generates a simple, plain radio wave. This is called the carrier wave. That's our delivery truck. It can go a long way, but right now it's empty. Next, we have to load our message, all those ones and zeros, onto the truck. That process is called modulation. And finally, the antenna acts like the shipping dock, sending that fully loaded truck out onto the invisible highway of the airwaves. Now, there are a bunch of ways to load that data onto the wave, but the two classics you've probably heard of are AM and FM. With amplitude modulation, you change the height or power of the wave to represent the data. With frequency modulation, you change how fast the wave oscillates, its frequency. FM is way more resistant to noise, which is why FM radio stations sound so much clearer than AM stations. Most static and interference messes with a wave's power, not its frequency. Okay, so our message is officially airborne. It's riding an invisible radio wave out of our device. And at this exact moment, it enters this massive, unbelievable global relay race that covers continents and crosses entire oceans. The first leg of this race is just a short sprint. Your phone connects to the nearest cell tower with the strongest signal and shoots its radio wave over. And as you move around, say in a car, your phone is seamlessly handing off that signal from one tower to the next, so you never even notice or drop the connection. As soon as it hits that cell tower, your message makes a huge leap. It jumps from the airwaves onto the physical, wired backbone of the entire internet. And we're not talking about old-school copper phone lines anymore. The modern internet runs on light, traveling through optical fiber, and the advantages are just massive. Fiber is totally immune to electrical interference, and a signal can travel over 80 kilometers before it needs a boost, compared to just 5 kilometers for copper. So how do you keep a beam of light trapped inside a tiny strand of glass for hundreds of kilometers? It's all thanks to this super cool principle from physics called total internal reflection. Think about skipping a stone across a lake. If you throw it at just the right shallow angle, it doesn't sink, it just bounces perfectly off the surface. That's basically what's happening to the light inside that fiber optic cable. It's just bouncing perfectly off the inner walls, trapped inside as it zips along for miles with almost zero signal loss. Okay, but now here's where things get really wild. Your message, that email, that video, it doesn't travel in one big piece. The internet chops it up into thousands of tiny little pieces called packets. It's like taking a book, tearing out every single page, putting each page into its own envelope with an address, and mailing them all separately. They might all take completely different routes to get there, but because each page is numbered, the book can be put back together perfectly at the other end. And when we talk about this being a global network, I really want you to get this one picture out of your head. A lot of people think our data is zipping around through satellites in space, but that's not really how it works. The truth is, over 95%, yes, 95% of all international internet traffic travels as pulses of light through these gigantic fiber optic cables lying on the bottom of the ocean, physically connecting the continents. So, after racing across the globe as radio waves and then as pulses of light, your message has finally arrived. And now that entire complex journey has to happen completely in reverse and has to do it in milliseconds. See, to get the information out of any kind of wave, you need one critical thing, a sensor, something that can catch that wave's energy and turn it back into a useful signal. A radio antenna does it for radio waves, a photodetector at the end of a fiber optic cable does it for light, and you know what? Our own eyes and ears are some of the most sophisticated biological sensors in existence. And for us humans, one sense is totally dominant. It's not even close. A staggering 80% of all the information we get from the world around us comes through our eyes. We are profoundly visual creatures, which is why that final step of translating data onto a screen is so important for us to actually understand the message. And finally, we've reached the end of the line. The journey is complete. The ones and zeros are fed into the receiver's device, where they're turned back into a smooth electrical wave. That wave makes the little speaker vibrate, and those vibrations recreate the original sound waves in the air. The sound that left your mouth on the other side of the world is now faithfully reproduced, ready to be heard. So, the technical journey is done, but converting that final sound back into something meaningful is the whole point, right? And this entire incredible process, it didn't just appear out of nowhere. It was built piece by piece, standing on the shoulders of giants. You can literally see the chain of progress, one discovery leading directly to the next. Morse showed us you could send information down a wire as electricity. Decades later, Maxwell, using just pure math, predicted that these invisible electromagnetic waves had to exist. Then, Hertz actually built a gadget that proved Maxwell was right. And finally, Marconi took that physics experiment and turned it into a practical system that could span the globe. Every single one of those steps was absolutely essential. But after exploring all of this incredible technology, it is so important to remember one thing. The medium is not the message. The most advanced fiber optic network in the world is completely useless if the message itself is confusing or sent at the wrong time or to the wrong person. The technology is just a tool. And that leaves us with one final big question to think about. We have achieved something that our ancestors could only have dreamed of: the power to send our thoughts to anyone, anywhere, almost instantly. But what's the ultimate purpose of that power? Are we using it to build deeper connections and real understanding? Or are we all just broadcasting, shouting into a bigger, more crowded room? The technology is here. How we choose to use it? Well, that's up to us.
You know, have you ever really thought about it? We're all basically swimming in this invisible ocean of information every single second of every day. It's not some kind of magic, it's physics. So today, we're going to pull back the curtain on this hidden world of waves and figure out how they carry everything, from your favorite song all the way to the light from distant stars.
So, here's what we're going to cover. First, we'll tackle the huge idea of waves as messengers. Then, we're going to crack their secret code. After that, we'll look at a really weird thing that light does, meet the geniuses who first harnessed the airwaves, and finally, we'll see how your own body is maybe the most amazing wave receiver ever built. Let's just dive right in.
All right, so let's get to it. Let's meet the main character of our story today, the wave. It's basically the universe's #1 delivery service for just about everything. I mean, really think about that for a second. There aren't any wires connecting the radio station to your car. There are no wires from your Wi-Fi router to your phone. So how? How is that even possible? What in the world is carrying all that information across empty space? Well, the answer is just so beautifully simple, and at the same time, it's incredibly powerful. It's waves. They are the invisible messengers, and they are carrying absolutely everything,
from the colors of a sunset to the data that's bringing you this explainer right now.
Okay, but, just having a messenger isn't really enough. You've got to be able to actually write a message on it. So how do we encode information onto a wave? Well, it turns out that waves have this kind of secret language, and it's got 3 main dialects.
First up, we've got amplitude modulation, or as you probably know it, AM. This one's the most straightforward of the bunch. You just change the power, or the height, of the wave. A really great way to think about it is like turning a volume knob up and down. That's how it represents information. It's the classic tech behind AM radio, and you can even use it for simple digital signals, where, say, a really powerful wave means a 1, and a weak one means a 0.
Next up is frequency modulation, or FM. Now, instead of changing the wave's power, here we're messing with its timing. Specifically, how many times it goes up and down per second. This is a lot like changing the pitch of a musical note, going from low to high. It's a much more robust method, way less prone to static and noise, which is exactly why your favorite music station on FM radio sounds so much cleaner than on AM.
And finally, we get to the really clever one, phase modulation. Okay, imagine a marching band, right? The beat, the frequency, it stays exactly the same. But then you suddenly tell one of the drummers to start on a different beat. That little shift, that hiccup in the pattern, that's how phase modulation encodes data. It's an incredibly efficient way to send complex information, and it's the secret sauce behind how your Wi-Fi can pack so much data into the airwaves.
So here's the big takeaway from all this. Early radio, it used the simplest trick in the book, just changing a wave's power. But to build the crazy, reliable, high-speed digital world we live in now, we had to get a lot smarter. We had to learn how to manipulate a wave's timing. And that leap, from focusing on power to focusing on timing, is what made everything from crisp FM radio to the super-fast Wi-Fi we all depend on possible. Okay, so we know how to write messages on waves, but what else can they do? Well, it turns out they have some really fascinating tricks up their sleeves. Let's take a look at one of their absolute weirdest behaviors, their ability to bend.
I mean, you've all seen this, right? You put any straight object, a spoon, a straw, whatever, into a glass of water, and it just magically looks like it's bent, or maybe even completely broken right there at the surface. So what's the deal? This isn't just an optical illusion. It's a fundamental property of how waves work.
This whole phenomenon is called refraction. And the secret to it all comes down to one thing: speed. When a wave, like a light wave, travels from one substance, like air, into a different one, like water, it actually changes its speed. And it's that sudden change in speed that forces it to pivot and change direction.
This slide just breaks it down perfectly. So, check this out. Look at that big wave front on the left. As it hits the water, but at an angle, the part of the wave that enters the water first, that's what you see in step 2, it suddenly slows down. It acts kind of like a brake. And that drag on one side causes the entire wave front to pivot, which changes its whole duration of travel. It's really just that simple difference in speed that creates the bend.
And this really shows just how common refraction is. It's not just some weird party trick you can do with a spoon. It's the reason we have rainbows, because raindrops are bending and splitting sunlight into all its different colors. It's literally how your eyeglasses work. They're bending light to focus it perfectly on your retina. It even explains things like desert mirages and why stars seem to twinkle. It's all just waves, changing speed.
So understanding the physics is one thing, but who were the brilliant minds that actually figured all this stuff out? The people who figured out how to use this knowledge to send signals across the entire planet. Well, this wasn't the work of just one person. It was more like a magnificent scientific relay race.
The race really started back in 1865 with James Clerk Maxwell. He predicted these invisible waves existed using nothing but math. Then, Heinrich Hertz picked up the baton in 1887 and actually proved Maxwell was right by creating radio waves in his lab. And finally, Guglielmo Marconi ran that final anchor leg. He used all that knowledge to send the very first signal across the Atlantic Ocean in 1901, and with that, he launched the wireless age we're all living in today.
Okay, so we've talked about the physics of waves, and we've talked about the technology we built to use them, but the most incredible wave receiver ever designed is the one you were born with. It's your own body.
Okay, get ready for this, because this number is just staggering. An estimated 80%, that's 80, of all the information you perceive from the world around you comes in through your eyes. We are, by a huge margin, visual creatures, constantly decoding the light waves that bounce off of everything.
Now, our other senses are super specialized receivers too. Our hearing is fine-tuned for communication, processing the pressure waves that we call sound. Touch is our most ancient and widespread sense, absolutely essential for survival. And then you have our chemical senses, smell and taste, which have their own unique and really powerful role. And what's so interesting is the direct line that smell has to our brain's memory and emotion centers. It's known as the Proustian memory phenomenon. A single scent can just unlock a flood of vivid, long-forgotten memories. It's a pretty powerful reminder of just how deeply all these signals are woven into who we are.
But here's the most amazing part. Our brain is adaptable. It's incredibly plastic. If one sense is lost, or even just diminished, the brain can literally rewire itself. It will dedicate more processing power to the remaining senses, making them sharper, more powerful. It is the ultimate information processor. So, when you step back and look at the whole picture, from the radio waves carrying this message, to the light waves letting you see your screen, to the sound waves entering your ears, it's all information, and it's all carried by these invisible messengers. The world is constantly broadcasting on every channel all the time. The only real question is, are you tuning in?
You know, you probably do it a dozen times a day without even thinking about it. You snap a photo, you tap share, and that's it. But have you ever really stopped to wonder what happens in that split second? Well, today we're going to follow the incredible journey of just one photograph, from a single particle of light all the way to becoming a permanent part of the global internet. So let's trace its path. I mean, it feels totally instant, right? 1 second, that picture's on your phone, and the next, your friend halfway across the world is looking at it. But wow, behind that one simple tap is this unbelievable, invisible journey. It involves physics, a hidden global network, and yeah, even a little bit of philosophy. So what really happens in that fraction of a second? We're going to follow that entire path, starting right at the beginning with the pure physics of how a camera even sees the world. It's a wild ride that transforms a physical thing, a particle of light, into something permanent in your digital life. Okay, so step one, how does that image actually get into your phone in the first place? Well, it all starts with light and some really, really clever physics happening inside that tiny little camera lens. So to get how your camera works, you got to know the difference between reflection and refraction. It's pretty simple. Mirrors reflect light. They just bounce it straight back. But your camera lens, and hey, your own eye for that matter, uses refraction. It actually bends the light as it passes through the glass. And to be specific, your phone uses what's called a convergent lens. Just think of it like a teeny tiny magnifying glass. Because it's thicker in the middle, it grabs all those scattered light rays coming from whatever you're taking a picture of and bends them perfectly so they all meet at a single point, the focus, right on your phone's camera sensor. Pretty neat, huh? All right, so the light has been perfectly focused onto the sensor. Now comes the first real piece of digital magic, turning that physical image into data that can actually leave your phone and travel the world. And this right here is the big leap. The moment that light hits the sensor, your phone's processor, its brain, sometimes called a system on a chip, just springs into action. It instantly translates that physical light signal into a digital file, into the language of ones and zeros that computers understand. So once that photo is a file, your phone basically turns into a tiny, sophisticated radio station. It sends out radio waves to connect to the nearest cell tower. That little SIM card you have, that's what tells the network, hey, this is me. And as you walk or drive around, your phone is constantly and seamlessly being handed off from one tower to the next. That cell tower is the first stop on our photo's global adventure. Okay, our photo made it to a local cell tower. That's great. But how in the world does it get from there to a server, maybe on another continent? Well, it's about to enter this hidden world of glass threads and laser pulses that make up the true backbone of our internet. Now get this, our photo, which started as light, is now converted back into light. But this time, it's an incredibly precise pulse of laser light, and it's shot through a fiber optic cable, which is literally a thread of ultra-pure glass that's thinner than a single one of your hairs. And the way this works is just brilliant physics. The light zips down this glass thread using a principle called total internal reflection. It just bounces perfectly off the inside walls of the glass, over and over again. It's like a perfect light tube. This lets it travel for thousands of miles with almost zero loss of signal. It's incredible. So just how important is this fiber optic network? Think about this for a second. Over 95% of all international internet traffic, your photo, your video calls, every single email, travels through these cables that are lying on the bottom of the ocean. You know, we think of the internet as being in the cloud, but it's really truly at the bottom of the sea. But here's where it gets even more clever. Your photo doesn't travel as one big clunky file. The internet uses this super robust system called packet switching. It chops your photo up into thousands of tiny little packets, slaps an address on each one, and sends them off. They might all take completely different routes through the network, but they all get put back together perfectly at the other end. It's what makes the internet so incredibly resilient. And how does each one of those little packets know exactly where to go? Well, it uses the internet's universal address book, called the Domain Name System, or DNS. The DNS is basically a translator. It takes the website name that we understand, like socialmedia.com, and turns it into a numerical IP address that computers can read. It's the GPS that guides every single packet to its final destination. So in less than a second, all those packets have arrived, they've been reassembled, and your photo is there. But the journey isn't really over. In fact, you could say the most important part is just beginning. Because by arriving, it has now become a permanent part of your digital identity. Every single photo, every comment, every like you make adds to your digital footprint. And we have to remember this. The internet doesn't really have a delete key. What seems private and shared just between a few friends today can be screenshotted, shared, and suddenly become permanent, public knowledge tomorrow. So, how do you manage this footprint? The basics are still the most powerful things you can do. Use strong, unique passwords for everything. Always, always turn on two-factor authentication. And actually take 5 minutes to go review the privacy settings on your accounts. These simple steps make a gigantic difference. And this goes beyond just protecting yourself. Being a good digital citizen means being mindful of other people too. Verifying information before you reshare it, and always, always respecting the privacy of the people in your photos. So when you step back and look at the whole thing, the journey is just, it's astonishing. A simple, everyday action directly connects the fundamental laws of physics with the really complex creation of our modern digital identity. We followed the whole transformation, right? It starts as physical light from the world around us. It's converted into binary data inside your phone. Then it's chopped up into packets that race across the globe as pulses of light in glass tubes. And finally, it's reassembled to become a permanent piece of your digital persona. From physics to persona, all in the blink of an eye. In all of this entire incredible journey, it leaves us with one really powerful question to ask ourselves before we hit share. Knowing the permanent journey your photo is about to take, would you be comfortable if your family, a future employer, or just any random stranger saw it? That's the real question, isn't it? Thanks for diving into this with me. Our digital lives are just full of these little choices that honestly have a huge impact. Are you sending the right message in the right way? Are you maybe a little too connected for your own good? Should your kid really have a phone in class? Today, we're going to break down 3 of these massive dilemmas of our modern world and hopefully help you figure out how to navigate it all. I mean, we've all been there, right? You send a quick, totally harmless text. Maybe something as simple as, okay, and the person on the other end reads it as you being cold or angry or dismissive. That simple, everyday misunderstanding, it's the perfect way to jump into our first big question. Because it's not just about what you say, it's about how you say it. Choosing between a text, a phone call, or a face-to-face chat can literally make or break a conversation. So how in the world do we choose the right tool for the job? Now, this is where it gets really interesting. What you're seeing here is a fundamental trade-off. Talking face-to-face is incredibly rich. You get tone of voice, you see their facial expressions, their body language. All that extra information helps you avoid misinterpretation, especially when you're talking about something sensitive. But on the other hand, writing gives you a superpower, time. You get to pause and craft the perfect response. The big downside, as we all know, is that it's stripped of all that emotional context. And that's exactly why a simple one-word text can start a massive fight. This whole idea is so important, it actually has a name. Media richness theory. Just think of it like a scale. On the rich end, you've got face-to-face conversations, perfect for complex, emotional, or ambiguous stuff. On the poor end, you have things like texts, which are great for simple, clear-cut info like, hey, I'm running 5 minutes late. The big takeaway here is that using the wrong medium for the message, like, say, breaking up with someone over text, isn't just bad manners, it's a complete communication mismatch. And of course, there's the modern compromise, the video call. It definitely brings back some of that crucial nonverbal information, which is great. But it comes at a price, something we've all come to know and dread as Zoom fatigue. Researchers say it's this unique exhaustion that comes from just staring at a grid of faces, trying to maintain this weird, forced eye contact with the screen for hours on end. So yeah, it's better than a text for a big team meeting, but let's be honest, it's still no substitute for actually being in the same room with people. So that leads us right into our second dilemma. We have all these incredible ways to communicate and stay in touch, but has it all just led to us being, well, too connected? We're all wrestling with this tricky balance between having constant access and feeling constantly overwhelmed. And the evidence for the downside is really starting to pile up. Study after study is suggesting strong links between heavy social media use and rising rates of anxiety and loneliness, especially for teenagers. The lines between our work and home life have completely blurred because the office is always right there in our pocket. We're constantly battling FOMO, that fear of missing out, which is just fueled by looking at the perfect highlight reels of everyone else's lives. And maybe the biggest one of all, our attention is being shattered into a million tiny pieces by the never-ending stream of notifications. This quote from author Cal Newport just absolutely nails the core problem. He argues that being in a state of constant low-grade distraction makes deep, focused thinking pretty much impossible. If your brain is always on standby, just waiting for that next ping or buzz, it can never really settle into the hard work of creating something new, solving a tough problem, or even just being present in the moment. But hold on, to be fair, the picture isn't all doom and gloom, not even close. The benefits of being so connected are literally world-changing. We have democratized access to information on a scale that's just unprecedented in all of human history. We can maintain deep, meaningful relationships with people across oceans. Marginalized groups have found community and a powerful voice, and we've seen entirely new forms of global collaboration and social movements spring up that just couldn't have existed before. So, what does that all mean? Well, maybe the problem isn't the technology itself. Maybe the real issue is our lack of control, our lack of agency over it. The goal probably isn't to just disconnect entirely, but to be more intentional, to actively choose when and how we connect, instead of just being passively dragged along by algorithms that are designed to do one thing, keep us scrolling. It's about being the master of the tool, not the other way around. And that idea of control brings us to our final, and maybe the most heated dilemma of all, the modern battleground of the classroom. Should cell phones be there at all? Are they a vital 21st century tool, or just the ultimate distraction? The arguments on both sides here are really compelling. On one hand, proponents say that banning phones is like trying to prepare students for a world that just doesn't exist anymore. They argue phones can be incredible tools for personalized learning and accessibility. But on the other hand, opponents see them as weapons of mass distraction, a vehicle for nonstop cyberbullying, and a major barrier to kids learning those crucial face-to-face social skills. And you know, the evidence against having them in class is getting pretty hard to ignore. We're seeing major studies with real, measurable consequences. A study from the London School of Economics found that test scores went up significantly after a phone ban. Research from the University of Texas found that just having your phone on your desk, even if it's turned off, lowers your available brain power because part of your mind is constantly working to not pick it up. It's really no wonder that huge organizations like UNESCO are now recommending global regulations. So after looking at how we talk to each other, how much we're all online, and where our phones belong, you start to see a pattern emerge, don't you? These aren't really technology problems. At their core, they're human problems. Really, what this all boils down to is that each one of these dilemmas forces us to choose between competing values. When it comes to communication, do we prioritize the sheer efficiency of a text or the depth of a real conversation? With our connectivity, are we chasing more and more interactions at the expense of our own well-being? And in our schools, do we prioritize preparing kids for the digital world as it is, or protecting their focus and social development right now? Ultimately, there are no easy one-size-fits-all answers here. These technologies are incredibly powerful, and they are not going away. So the question we're all left with isn't really about what the tech can do, it's about what we want it to do for us. It's all about consciously, intentionally deciding what kind of life, what kind of focus, and what kind of relationships we want to build in this crazy connected world. So what's your choice going to be? Today, we're going to talk about something so fundamental. You see it every single day. We're diving into a simple, elegant rule that explains everything from your own reflection to how the Wi-Fi signal is getting to your screen right now. So let me ask you this. What could your eyes possibly have in common with your Wi-Fi router? I know, it sounds like a weird riddle, right? But the answer, well, it gets to the very heart of how information itself moves through the universe. The answer is they are both receivers, built to catch and decode information that travels in the form of waves. And that really gets at the biggest challenge of communication. How do you send a message, an idea, a picture, a sound, without physically mailing an object from one place to another? Well, the solution is you have to use the language of waves. Okay, so here's the absolute core idea you need to get. Information itself, it has no substance. The words I'm saying right now, you can't hold them in your hand. So to send that information across a room or even across the planet, it has to be piggybacked or encoded onto something that is physical, a wave of energy. And this whole process follows these same 4 steps, no matter what. First, you have transduction. That's just turning the information into an electrical signal. Second, that signal gets encoded onto a wave, like a radio wave. Third, the wave propagates, which is just a fancy word for travels, through space. And finally, reception. That's where something like an antenna or, your eye catches the wave and decodes the message. And that last step, reception, that's not just for technology. We all walk around with these incredibly advanced built-in wave detectors that we are using every single second of the day. We just call them our senses. But here's the thing. One of those senses is an absolute beast. It's estimated that a whopping 80% of all the sensory information that our brain deals with comes from just one single source. Yeah, look at that. Sight just completely dominates how we perceive the world. It processes the vast, vast majority of all the data coming in. And that's exactly why, if we want to understand the rules of waves, we're going to focus on the one our eyes were built for: light. You can really think of our 2 main receivers, sight and hearing, as a perfect team. Sight is our master of electromagnetic waves, light, and it gives us this incredible map of the world around us. Hearing, on the other hand, detects mechanical waves, sound, and it's amazing for things like language. Together, they work to build the reality that we experience. So it's no surprise that this obsession with trying to understand and control light has led to its very own dedicated field of science. And that field is called optics. It's the whole branch of physics that studies everything there is to know about light, how it moves, what it's made of, and, crucially, how we can build things to control it, everything from a simple pair of glasses to the James Webb Space Telescope. Now, optics kind of splits into 2 main camps. There's physical optics, which gets really deep into the weeds, treating light like the complex wave it is. But for most everyday stuff like mirrors and lenses, we can use something way simpler, but just as powerful. It's called geometric optics, and it just pretends light travels in perfectly straight lines, which we call rays. And by using just those simple, straight lines, we can create this amazing tool called a ray diagram. It's basically just a drawing, but it lets us predict exactly where a beam of light is going to go. In fact, let's build one together, right now. Okay, first things first, we start with our surface. This vertical line you see the little hatch marks on the right side, that represents a simple plane mirror. Just a totally flat, reflective surface. All right, now we need some light. This arrow here represents a single ray of light heading towards the mirror. We call this the incident ray. Think of it as the incoming ray. Now, this next part is maybe the most important piece of the whole puzzle. Right at the exact point where that light ray hits the mirror, we draw a dashed line. This line has to be at a perfect 90-degree angle to the mirror's surface. It's an imaginary line, but it's the key to everything. We call it the normal. So, the light hits the mirror, and what happens? It bounces off, right? This arrow, the one pointing away from the mirror, shows us the path that light takes. This is our reflected ray. And last, we just need to label the 2 angles that really matter. The angle between the incoming ray and that normal line, that's the angle of incidence, or theta I. And the angle between the outgoing ray and the normal, that's the angle of reflection, theta R. Now notice, this is super important. We're always measuring from the normal, not from the surface of the mirror itself. And there you have it, a complete ray diagram. What's so amazing is that this simple little drawing we just made actually reveals a profound universal law of physics, a law that governs every single reflection happening anywhere in the universe. The law itself is just beautiful, and it's something people have understood for ages.
all the way back to the ancient Greek mathematician Euclid. It's simply this: the angle of incidence equals the angle of reflection, every single time.
That's it. It all comes down to this one perfectly simple equation: theta I equals theta r. The angle the light comes in at is always the same as the angle it leaves at. That's the whole law. Now, this simple law is what explains why a mirror looks shiny, but your wall doesn't. On a super smooth surface, like a mirror, all the light rays come in together, and they all bounce off in the same direction. We call that specular reflection. But on a rough surface, like a wall, that same law still applies to every single tiny point. But because the surface is all bumpy, the rays scatter in a million different directions. That's diffuse reflection. So let's just pull all that together. We started with this idea that information, well, it travels in waves. We realized that our own senses are these amazing biological wave detectors, and that our eyes are doing most of the heavy lifting. And then we discovered that all of sight, all of reflection, is run by one incredibly simple and predictable rule: the angle in always equals the angle out. And that leaves us with one last kind of mind-bending thought. Our senses only evolved to pick up on a tiny, tiny slice of all the waves that are flying around us all the time. So if our entire reality is just the story being told by the waves we happen to be able to decode, what other stories are out there? What are we not detecting? So we all know that light travels in a straight line, right? Well, yeah, until it doesn't. And that moment, when we bend it, when we control it, that's where all the magic happens. In this explainer, we're jumping right into the world of mirrors and lenses to see exactly how we manipulate light. And then we'll uncover that final crucial step: how we actually capture it to create an image we can see. Let's kick things off with a mystery you've probably seen 1,000 times. That little warning on your car's passenger side mirror. Why is it even there? What does it mean? I promise you, the answer unlocks the key principles of how we bend light, and by the end of this, you'll know exactly why it's there. So where does the answer lie? Well, it all starts with mirrors, but not your typical flat bathroom mirror. Nope, we need to talk about curved mirrors, the kind that can totally trick your eyes by changing the size and even the perceived distance of everything they reflect. Okay, so we've basically got two main players in this game. First up is the concave mirror. The easiest way to remember it is that it curves inward, like a cave, or a bowl. Its job is to gather light and bring it all together. And then you have its opposite, the convex mirror. This one bulges outward, kind of like the back of a spoon. And it does the exact opposite. It spreads all the light rays apart. Now, you might think you need a ton of complicated math to figure out what an image in one of these mirrors will look like. But here's the wild part. You don't. You just have to follow these 3 simple rules of how light behaves. By tracing these key rays of light, we can map out exactly where an image is going to form and what it's going to look like. It's almost like a geometric cheat code for optics. Pretty cool, right? So once we've tracked down that image, we need a way to talk about it. This is basically our vocabulary. There are just 3 questions we have to answer. First, its size. Is it bigger or smaller? Magnified or diminished? Second, its orientation. Is it right side up or upside down? Upright or inverted? And finally, is it real? Meaning, could you project it onto a screen? Or is it virtual? Something that only looks like it's behind the mirror? These 3 properties tell us the whole story. And this is where concave mirrors get really, really versatile. Just look at this table. Depending on how far away you put an object, you get totally different results. If it's far away, you get a tiny upside-down image, perfect for a telescope. Bring it a bit closer, and suddenly the image gets bigger and stays inverted. That's how a projector works. And if you get really close, right inside that focal point, boom, you get a magnified, upright image. You're looking at your makeup or shaving mirror. Okay, so what about our other mirror, the convex one? Well, unlike its complicated cousin, the convex mirror is incredibly predictable. I mean, it doesn't matter where you put something in front of it. The image is always going to be virtual, upright, and smaller than the real thing. Always. And that consistency, well, that's its superpower. And that right there brilliantly solves our car mirror mystery. Because the convex mirror makes everything look smaller or diminished. It can squash a much bigger scene into its reflection. This massive field of view is a lifesaver for seeing more of the road and getting rid of blind spots. But what's the trade-off? By making other cars look smaller, it also tricks our brains into thinking they're farther away than they really are. Mystery solved. So that's what happens when light bounces off of a surface. But what about when it goes through something, like a piece of glass? Now we're leaving the world of reflection and entering the world of refraction and lenses. The magic word here is refraction. A great way to think about it is like a car driving from a paved road straight into a patch of mud. What happens? It slows down and kind of veers off in a new direction. Light does the exact same thing when it goes from air into glass. That change in speed forces it to bend. And literally every lens you can think of, from eyeglasses to a giant telescope, is built on this one simple idea. And guess what? Just like with mirrors, we have two main kinds of lenses. A convex lens, which is fatter in the middle, brings light together or converges it. You might notice that sounds a lot like a concave mirror. And a concave lens, which is thinner in the middle, spreads light out or diverges it, just like a convex mirror. See, the physics kind of rhyme, which makes it way easier to remember. The convex lens is really the workhorse of the optics world. Just look at what this thing can do. If an object is far away, it makes a small, real, inverted image. That's how a camera and your eye works. If the object's a bit closer, you get a large, real, inverted image. Hello, movie projector. And when you bring an object super close, you get a large, upright, virtual image. Yep, that's a magnifying glass. Okay, this is where things get really personal. We can actually put a number on how much a lens bends light. And this isn't just some abstract physics concept. It's the key to understanding your very own eyeglass prescription. And it all boils down to this wonderfully simple formula. Power equals 1 divided by the focal length, or P equals 1 over F. So you can see right away, a lens that bends light really sharply will have a short focal length, which means it has a really high power. We measure that power in a special unit called the diopter. So when your optician gives you a prescription with a number on it, like +2 or -3, that number is in diopters. It's a direct measure of how strong that lens is. And the best part? That little plus or minus sign tells you everything you need to know. If it's a positive number, it's a converging, convex lens, the kind that corrects for long-sightedness. If it's a negative number, it's a diverging, concave lens, which is for short-sightedness. It really is that straightforward. Let's try to decode a real one. Let's say you've got a pair of reading glasses that say +2.5 diopters. We just flip our formula around. Focal length equals 1 divided by the power. So we plug in the number, 1 divided by 2.5, and what do we get? 0.4 meters, or 40 centimeters. That means that lens brings light to a perfect focus at a distance of 40 centimeters. You could totally do this with your own prescription. So, we did it. We bent light with mirrors, we focused it with lenses, and we formed a perfect image. Job done, right? Well, not quite. We are missing one final, absolutely critical piece of the puzzle. You see, an image just floating there in space is totally useless unless something is there to actually detect it. Forming the image is only half the story. And this leads us to a fundamental truth about everything, really. You can shape a signal, you can focus it, you can transmit it perfectly, but if there's nothing on the other end to receive it and interpret it, that information is just gone. As the slide says, no sensor equals no detection. End of story. And these sensors are everywhere once you start looking for them. They're all just translators. Your eye translates light into nerve impulses. A camera sensor translates photons into digital pixels. A radio antenna translates radio waves into an electrical current. Even your ear, it's just a sensor that translates pressure waves in the air, sound, into signals your brain can make sense of. This slide really puts it all together for us. This is the complete communication chain. Our mirrors and lenses, they're doing their job back in step 3, transmitting and focusing the wave. But as you can see, without step 4, without that sensor to actually detect the wave, the entire chain is broken. You need every single one of these links to get from the source all the way to the final output that you actually perceive. And that kind of leaves us with this one last big idea. Our eyes are incredible sensors, for sure, but they are tuned to see only a teeny tiny slice of all the light that's out there, what we call the visible spectrum. Radio waves, microwaves, infrared, ultraviolet, all of that is light. All of it is carrying information all around us, all the time. Which has to make you wonder, what else are we just not seeing? What other worlds are hiding right there in plain sight, just waiting for the right sensor to see them?
You know, we humans have this deep, fundamental need, right? To send a message, to get an idea from my head to yours, even if we're miles apart. It's this epic journey that started with something as simple as a flickering flame. And now? Well, now it rides on invisible waves that connect our entire planet. So let's trace that amazing story.
In the very beginning, it all started with the most basic elements you can imagine. The carrier of our message? It was just smoke, a simple puff on the horizon.
Then we found sound. Rhythmic beats, drums carrying complex messages clear across entire valleys.
From there, we figured out how to harness light itself, flashing signals from one tower to the next.
And then, everything changed. The first real revolution, trapping our messages and sending them as tiny pulses down a wire.
Until finally, the ultimate leap of faith, sending information through thin air itself, riding on invisible waves.
Okay, so smoke signals and electrical wires. I mean, they seem like they're from different planets, right? But believe it or not, they all share one core universal challenge.
And that challenge is something called information encoding. Honestly, this is the key that unlocks everything. It's just the process of turning an idea, a thought, into some kind of physical signal that can actually travel through space. And it doesn't matter if it's a puff of smoke or a digital bit on your phone, the basic logic is exactly the same.
And you can see this idea pop up all throughout history. I mean, think way back, 1,000,000 years ago, a simple pattern of smoke meant danger. Then you've got the incredible complexity of West African talking drums, which could literally encode entire languages into just rhythm and pitch. So cool. And then, fast forward to the 1790s, you've got this ingenious optical telegraph with mechanical arms spelling out letters, flashing messages across France in just minutes. See, the technology gets more and more clever, but that core idea of encoding, it never changed.
But then, something happened that would completely change the game. The first great revolution. It was time to harness electricity and conquer the wire.
And it's hard to overstate just how huge this was. Before this, you were basically trapped by physics. Your message could only go as far as someone could see your smoke or hear your drum. You were limited by the line of sight, by the speed of sound. But with electricity, suddenly, the only real limit was how long you could make the wire. That's it, a total game changer.
So who do we have to thank for this? Well, two pioneers really stand out. First up, you've got Samuel Morse. In 1837, he's the one who proved you could take complex information, letters, numbers, the whole shebang, and encode it into simple little electrical pulses. Yep, his famous dots and dashes. But then, almost 40 years later, Alexander Graham Bell does something that must have seemed like pure magic. He figures out how to transmit the actual, continuous wave of a human voice as an electrical signal. Incredible.
Okay, so the wired world was pretty incredible, right? But the next challenge was even bigger. The question became, how do you get rid of the wire completely? Well, get ready, because this is the story of the wireless revolution.
Now, what's so fascinating is that this revolution didn't start in a lab with sparks and machines. Nope, it started in the mind of a physicist, James Clerk Maxwell. Back in 1865, using nothing but pure mathematics, he predicted that these things called electromagnetic waves had to exist and that they would travel at the speed of light. It was just an idea on paper, a theory, but it was a theory that whispered, hey, wireless communication, it should be possible.
But that's a pretty wild idea, right? It left the entire scientific community wrestling with this massive question. Could an invisible wave really just travel through empty space and carry a message with it?
And the answer came in this beautiful, classic chain of scientific progress. It's like a relay race. First, Maxwell's theory predicted the waves. Then, 22 years later, Heinrich Hertz grabs the baton and builds an experiment that actually proves they exist. He literally created and detected them in his lab. And then, Guglielmo Marconi takes that proof and runs the final lap, turning it into a practical application, the first working wireless system. Theory to proof to application. That right there is how science becomes the technology we use every day.
Okay, so that's the history. But how does this stuff actually work? Let's dive into the physics of how you send a message right through the air. Well, it all starts with what we call the electromagnetic spectrum. And the craziest thing is that radio waves, the light you're seeing with right now, and even X-rays, they're all fundamentally the same thing. They're just light with different frequencies or different energy levels. Radio waves hang out on the low-frequency, low-energy end of the spectrum, and that's what makes them so perfect for communication. They can travel super long distances and even pass right through things like walls. So, how do we get, say, your voice to ride on one of those waves? It's basically a 5-step recipe. Step 1. A microphone turns your voice into a little electrical signal. Step 2. A gadget called an oscillator creates a steady, high-frequency carrier wave. Step 3, and this is the magic part.
A process called modulation basically piggybacks your voice signal onto that carrier wave. Step 4, an antenna blasts that combined signal out into the world. And finally, step 5, a receiver somewhere else catches that wave and decodes it, getting your voice back. Simple as that. Now that magic part, the encoding or modulation, mostly happens in two ways you've definitely heard of, AM and FM. With amplitude modulation, AM, you're changing the height of that carrier wave to match the sound of your voice. The wave gets taller and shorter. But with frequency modulation, FM, the wave's height stays the same. Instead, you're changing how close together the waves are, their frequency.
Okay, so why should you care? Why does this even matter when you're just trying to listen to music in your car? Well, it all comes down to noise and static. See, most interference in the air, from lightning, from power lines, messes with a wave's height, its amplitude. Since AM puts the information right there in the amplitude, it's really easy for it to get staticky. But FM? It hides the information in the frequency, which doesn't get messed with as much. And that's exactly why FM radio generally sounds so much clearer and higher quality, even if an AM signal can sometimes travel a little farther.
So all this history, all this science from over 100 years ago, it isn't just a story for a textbook. It is literally the foundation of our modern connected lives. It's the wireless world, and its legacy is probably sitting in your pocket right now.
I mean, just think about it for a second. Your Wi-Fi, GPS, Bluetooth, your cell phone, satellite TV, even your TV remote. Every single one of those modern marvels works on the exact same principles discovered way back when by Maxwell, Hertz, and Marconi. They're all just encoding information onto electromagnetic waves and sending it through the air.
So, when you really step back and look at the whole story, it is an absolutely incredible journey, isn't it? We went from encoding simple messages and patterns of smoke to encoding vast amounts of data onto invisible waves that bring us pictures from the deepest corners of space. It just makes you wonder, what's next? What will be our next carrier?
Let's dive right in. Today, we're pulling back the curtain on the physics of information. We're talking about the invisible rules and incredible engineering that lets you watch a video from the other side of the planet, basically instantly. Believe me, it's not magic, it's something way more interesting.
So seriously, how does that happen? It feels like it just appears, but it's actually part of a remarkable chain of technology. We're going to follow a single piece of information on its epic journey, from a massive global network right down to the atomic level.
You know, to send any kind of information over a long distance, we've really only got two fundamental choices. We can either send it wirelessly through the air, or we can guide it physically through some kind of cable. And as you'll see, each one has its own unique pros and cons.
So here's the core trade-off, right? Sending a signal through the air with radio waves is amazing. It gives us total freedom, no wires. But guiding that signal through a physical wire, like an internet cable, well, that gives your information a private, dedicated highway all to itself.
The biggest headache with radio is that the air is a shared space. Think of it like a giant, crowded room where everyone's trying to talk at once. The radio spectrum is a limited resource, so it gets jammed up, and that leads to interference. And just like shouting, your signal gets weaker and weaker the farther it has to go. It's fantastic for being on the move, but for sending huge amounts of data reliably, we needed something better.
So if radio has its limits, what's the heavy-duty alternative? What do we use to build the high-speed backbone of the entire internet? Well, the answer, incredibly, is found inside a tiny, hair-thin strand of super pure glass, all thanks to a really cool physics trick that lets us trap light itself. The whole thing works because of this beautiful principle called total internal reflection. It's this fascinating property of light where, if you get the conditions just right, the boundary between the glass and the air outside acts like a perfect mirror. And I mean perfect. 100% of the light gets reflected back inside. Nothing escapes. So how do you pull off this trick? Well, it's all about the angle. If a light ray hits the inside wall of the glass at a shallow angle, it just leaks out. No good. But if you make that angle steep enough, past a specific point we call the critical angle, bam, the light is completely trapped. It just bounces perfectly off the inside wall, zigzagging down the fiber for miles and miles. And the payoff for using this trick is just staggering. By sending our data as pulses of light in glass instead of electricity in copper, we don't just get a little faster, we get a monumental leap. We jump from gigabits to terabits of bandwidth. That's 1,000 times more capacity. And the signal can go over 100 kilometers before it needs a boost.
Oh, and since it's light, it's completely immune to electrical interference. This is exactly why fiber optics form the backbone of our entire global internet. Okay, so we've got this incredible, super fast pipe. That's amazing, but that's only half of the revolution. The other half wasn't just how we send information, but the very language we use to write it down. This was the game-changing shift from analog to digital. Think of it like this. An analog signal, like the groove on a vinyl record, is a direct, continuous, physical copy of the original sound wave. The groove literally looks like the sound. But a digital signal, it's not a copy at all. It's a description. It's a precise recipe written down as a long, long list of numbers. And right there, that leads to the single most powerful advantage of going digital. When you copy an analog tape, you always add a little bit of noise, a little bit of hiss. The copy is always just a little bit worse than the original. But when you copy a digital file, you're just copying a list of numbers. The copy isn't just good, it's perfect, flawless, every single time. So converting from the real, messy analog world to the clean, perfect digital world happens in a few steps. First, we sample the sound wave, which just means we measure its height thousands of times every second. Then we quantize those measurements. Think of it like rounding to the nearest whole number. We just snap each measurement to a pre-approved level. And finally, we encode each of those levels as its own unique string of ones and zeros. Okay, so now everything is a long list of ones and zeros. Awesome. But that's still just an idea. How do you physically build a machine that can actually understand, store, and process them? Well, you need the simplest physical object you can imagine, a basic on-off switch. And folks, here is the hero of our story, the transistor. It is, without a doubt, one of the most important inventions in human history. It's a beautifully simple idea, a microscopic switch with absolutely no moving parts that you can flip on or off with just a tiny pulse of electricity. And this right here is the crucial connection. The physical state of that tiny transistor, whether current is flowing or not flowing, directly represents the abstract binary digits 1 and 0. An on transistor represents a 1. An off transistor represents a 0. That's it. That's the entire language. Now this is where it gets truly mind-bending. Thanks to decades of just unbelievable engineering, we can now pack billions of these little switches onto a chip the size of your fingernail. A modern computer processor has something like 25 billion transistors. That's 25 billion individual on-off switches all working together. So what on earth do you do with billions of switches? Well, pretty much everything. You configure them in different ways to hold a state, a 1 or a 0, and that becomes memory. You wire them together into clever circuits called logic gates, and now they can do math. And you use them to create the little electrical pulses that send all those ones and zeros out into the world. So now we have all the pieces. We've got the glass fiber, we've got the language of ones and zeros, and we've got the tiny switches that speak it. So let's put it all together and trace the full journey of our information, from a real-world signal all the way to a screen on the other side of the planet. So it all starts when a sound, like your voice, gets digitized into a stream of ones and zeros. The billions of transistors in your device process that data and use it to flash a tiny laser on and off incredibly fast. Those pulses of light, that's your data, travel through a fiber optic cable, bouncing their way across continents in the blink of an eye. At the other end, a receiver sees those light pulses, converts them back into ones and zeros, and its transistors turn that code back into the original sound. From your mouth to their ear, in an instant. And that brings us to our final, kind of wild thought. The gates on these transistors, the part that does the switching, are now so small they're only a few atoms across. We are literally hitting the fundamental physical limit of this technology. So the question we'll leave you with is, what comes next? What will be the switch that powers the next information revolution? Will it be based on the strange rules of quantum computing, or something else entirely we haven't even dreamed of yet?
You ever just stop and think about the absolute magic happening inside the technology we use every single day? I mean, from the phone in your hand to the invisible networks that connect all of us, there's this incredible story unfolding literally all the time. Today, we're going to pull back the curtain and unravel some of that magic. Let's get into it.
It feels completely instant, doesn't it? You tap a screen and boom, music just fills the room. But in that tiny fraction of a second, an unbelievable chain of events kicks off. So in this explainer, we're going to follow that single tap on its journey, step by step, to see exactly how it all works.
All right, so before a single note of music can even think about playing, your request needs some serious processing power. And all of that happens inside a device that just a few decades ago would have sounded like pure science fiction. This massive leap forward, it's really all thanks to one simple observation that completely changed the world.
And what you're looking at here, this is basically Moore's Law in action. See, way back in 1965, Intel's co-founder Gordon Moore noticed that the number of transistors we could cram onto a chip was doubling about every 2 years. Now, this wasn't some law of physics, but his prediction became the engine driving the entire tech industry. Just look at those numbers. We went from thousands to millions to billions. It's staggering.
And this right here really shows you the real-world impact of that. The same trend that gave us exponential power also made everything smaller and cheaper. I mean, what used to take up an entire air-conditioned room with a whole team of engineers now just sits quietly in your pocket, waiting for you to tap play.
But, that kind of crazy growth can't go on forever. We're now building transistors that are just 2 or 3 nanometers wide. To put that in perspective, that's smaller than a virus. We are literally bumping up against the physical limits of matter itself. And that's exactly why the industry is now exploring these mind-bending new ideas, like quantum computing, to find a way to keep pushing forward.
Okay, so your phone has all this incredible power, but what is a digital song file anyway? How do you actually take a real physical sound wave, this smooth, continuous analog thing, and translate it into the ones and zeros that your device can actually understand?
Well, the secret ingredient here is a concept called the sample rate. The easiest way to think about it is like this. You're taking a super fast series of snapshots of a sound wave. And the more of these snapshots you take every second, the more accurate your final digital picture of that sound is going to be. And there's a perfect way to visualize this. Imagine you're trying to draw a big, moving ocean wave, but the only way you can do it is by taking pictures of it, right? If you only take one photo every minute, your final drawing is going to look really choppy and, frankly, not much like a wave. But what if you took thousands of photos every single second? You'd be able to perfectly recreate the smooth, beautiful motion of that wave. That is exactly what sampling does for sound. And this is why different types of audio have such different quality. A phone call? It only needs about 8,000 snapshots a second for us to understand a voice. But for really high-quality music, like on a CD, you need 44,100 samples every single second. Basically, the rule is you need to sample at least twice as fast as the highest sound you want to capture. Since we humans can hear up to about 20,000 hertz, that 44,100 rate gives you a flawless digital copy of the music.
So, we've got a super powerful device, and we have a perfect, high-quality digital file. Now what? We need to get that file from a server somewhere out there on the internet. And to do that, your phone has to reach out through the air, sending a request across the mobile network. But how in the world does that actually happen?
It all starts with the cell in cell phone. I love this. The entire world is basically divided up into these geographic zones, or cells, and each one has a tower sitting right in the middle of it. Your phone is constantly scanning for these towers, and it always connects to whichever one has the strongest signal, just to make sure you have the best possible connection.
So when you hit play, your phone zaps a radio signal to that closest tower. Now, the tower itself doesn't do any thinking. It's just a relay. It passes your message along, usually through fiber optic cables, to your provider's core network. That's the real brain of the whole operation. It figures out who you are, what you want, and where in the world it needs to send you requests for that song.
And the reason we can stream a song instantly is all thanks to the insane evolution of these networks. Remember 2G? Man, that could barely handle a text message. Then 3G gave us our first taste of the internet on the go. 4G is what really made video streaming on your phone a normal thing. And now, with 5G, we're opening the door to a world where basically everything is connected, all the time, instantly.
Okay, so the mobile network is like the local on-ramp, right? It gets your requests moving. But where is that on-ramp actually heading? Well, it's merging onto the internet's global road system, this massive network of networks that stretches across the entire planet.
Let's think about it this way. Your Wi-Fi network at home? That's a local area network, or a LAN. It's kind of like the private streets of your own little city. All your devices, your phone, your laptop, your smart TV, they're all connected here, talking to each other quickly and securely. But to go get that song from a server halfway around the world, you have to leave your local streets and get on the highway. That's the Wide Area Network, or WAN. It's what connects all those individual little LANs together. And the internet? Well, that's the ultimate WAN, a global grid of high-speed fiber optic cables, with thousands of miles of them running under the ocean, connecting whole continents.
And the device that manages this whole transition is your router. And I love this quote because it says it perfectly. Your router is the customs agent for your data. It acts as a firewall, protecting your private little city from the wild west of the public internet. And it translates all the addresses so your request can travel the globe and find its way right back to the specific device that asked for it.
So we've just walked through 4 distinct, incredibly powerful technologies. But the real magic, the part that's easy to forget, is how they all work together in this perfectly seamless, invisible dance every single time you pick up your phone. So let's bring it all home and go back to our original question.
When you tap play, what you're really doing is conducting a technological symphony. Moore's law gives your device the raw brain power to even make the request. The concept of sample rate ensures the song file itself is a perfect, high-fidelity copy of the original recording. The mobile network then beams your request wirelessly out into the world. And finally, the massive global road system of LANs and WANs fetches that file and delivers it right back to you, all of it happening in less time than it takes you to blink.
It's just an incredible system, isn't it? All built on decades of relentless, brilliant innovation. And that brings us to one final thought. We've seen how Moore's law was the fuel for this entire digital revolution, but we also know it's starting to slow down. So the real question we're left with is, what's next? What new breakthrough, what new pillar of technology is going to come along and redefine our world all over again?